Ready to listen to the lecture?
Yes, sir.
Yes.
Yes, sir.
Do you remember what we did last time? Does anyone remember? What was done in the last class? No? Okay, so then let's review it a bit. So, for the last several classes, we have been reviewing different or learning about tools which will help us to actually study granular materials and granular flows in a nice way. So, we first started with vectors and tensors. Then we looked at numerical simulation of granular flows. And the first method that we looked at was hard particle simulations. And in the last class, we started talking about soft particle simulations. So really, this is what we had done. And I showed you, some examples. These are all now uploaded. I mean, at least some of these have been uploaded on Moodle. So the basic idea is this, that you have n particles in a box whose mass is mi, moment of inertia is capital Mi. Their position, velocity, and angular velocities are given, let's say at the initial time. And then there are forces acting on the particle like gravity, and then interparticle forces, and if you have friction, then torques also. So we are developing equations initially only for frictionless particles. So in this case, the angular velocity, the moment of inertia, and the torque not required. And our governing equations are simply this. That is, mass into acceleration is sum of all the forces plus sum of the interparticle forces plus gravity force. And the rate of change of position of a particle is just equal to its velocity. So here Fij is the force exerted by particle j on particle I, and g is acceleration due to gravity. So there may be more than one particle exerting, more than one particle j exerting a force on particle I. So that's why you have a summation. And this n is from 1 to n, but most of these forces will be zero. Only a sum of the particles will exert force on it. So we did this by hard particle simulations in which the collisions are instantaneous. And then we started talking about this soft particle method, where I'm going to show you the equations only for frictionless particles. And we saw last time that when the force is Fij is non-zero only when the two particles are in contact like this, where xi and xj are the vectors corresponding to the centers of the particles. And for this case, the force is just given by two terms. This is the spring force, and then this is the viscous dissipation. And kx and kv are two constants. Vn is the relative normal velocity, and n is a unit vector that is along the line joining the centers of the particles. So this is xi minus xj divided by the magnitude of the vector. So that's why it becomes a unit vector. So this is the simple force model. And of course, we have Fij is equal to 0 if alpha is less than 0. Alpha less than 0 means that the particles are not touching. Alpha is essentially just the distance. This distance is basically alpha. So it's positive if the particles are overlapping, becomes 0 when they're just touching, and if the particles are apart, then it will be less than 0. So in that case, Fij is just equal to 0. Okay. And then for this model, we saw that you can calculate the coefficient of restitution like this. You can calculate the time for a collision like this. And here A is just kV divided by 2 and B is kx minus kV squared by 4 raised to the power of half, where kV is, now if we put kV equal to 0, that means A is equal to 0, and you have here exponential of 0, which is 1. So that's why the coefficient of restitution is 1 when there is no viscous dissipation. So no energy lost means now that was the force acting. Now how do we actually do the simulation? First, we compute and store the neighbor list, which is particles closer than some specified distance. You know, in the class we had used the term RNG. Then look at what are the interparticle forces Ij using this neighbor list. So once you have calculated the forces, then update the particle positions and velocities integrating over the time step dt. And the simplest algorithm is the Euler algorithm, where it says that the position at x of t plus dt is the position at time plus velocity at time t into dt, and the velocity at any time t plus dt is just this. Of course, this is divided by the mass, but since we have made everything dimensionless, mass is 1, that's why. So the change in velocity is just acceleration multiplied by the time step dt. And usually you can calculate the t collision from the formula in the previous slide and then divide that by 50 to get what should be the time step. So this is the method, this is the algorithm. Now if you just get into a little bit of detail, and these programs are there, and we saw how one of them runs. So as I had mentioned in the last class, that the most expensive in terms of computation, the thing that takes maximum time is this computation of the neighbor list. And so how do you find out the neighbor list? Well, you loop over the particles. This is the crude way of doing it. You go I going from 1 to the number of particles, and j going from I plus 1 to the number of particles. You calculate the distance, which is xi minus xj whole squared. And if this distance is less than the value range, then this particle I is a neighbor of j. So what we write is n, the number of neighbors of j is increased by 1, and the n neighbor j, so this number of the particle j is equal to I. So n neighbor of j is the number of neighbors of particle j, and this matrix NEB of j comma n, it simply tells you the particle number I of the nth neighbor of j. Now since we don't want to store everything double, that's why we always take I to be less than j, and n always has to be less than or equal to the total number of neighbors of that particle. So you can see this is the way that we can store the neighbor list, and this calculation requires the square of the number of particles by 2, so many computational steps. So if as your particles number increases, so you'll go to If you have 10 particles, you'll have to do 100, which is not bad. But if you have a million particles, then you'll have 10 raised to power 12 computational steps, and that's finished. I mean, you won't be able to do it. Because remember, we have to calculate this quite often. Now, to save our computation, we had discussed a little bit that what should be the number of time steps that you can go before you calculate the neighbor list again. So now this depends on this parameter RNG, because you're calculating all neighbors, all particles which are within this dotted line. Those are the neighbors of particle I. This is J, which is the neighbor of particle I. And so, we can see that the maximum distance that a particle will move will be Vmax into 50. Let's say if we are calculating the neighbor list every 50 steps into dt. And if this value is less than range -1, that is this distance between the dashed line and the dotted line, then you're okay. If it becomes greater than, then you will miss out on some of the collisions. So this number 50 depends on what is the value of range you have taken, and also it depends on the Vmax. So you have to do a little bit of optimization, and we saw that also in the previous class. I want to now introduce one more way of introducing some computational efficiency, and that is mainly an easier way of calculating the neighbor list. And this is, oh sorry, before that I go to this. So in the last class you will remember that I showed you that when I ran the program, the velocities all blew up, and the reason is that the time step was so big that the computation became unstable. So you can actually do one thing that will make the computation more robust. That is, the program will not blow up. It will not become unstable. If you use something like a predictor character method. This is very commonly used in integration of differential equations, because always the question is what should be this time step dt. And if you have a time varying flow and things like this, it's difficult to put a constant dt and carry on. So what you can do is you can actually do two calculations. So first you can use a constant time step dt. So we call it as a single step calculation. So you'll get xi prime and vi prime by doing this, as we had seen before. And so if you look at qualitatively, then when we go, let's say we start at this point, we calculate the slope of f, and it turns out to be this, and then we take a time step dt, and we'll end up over here. Okay, so this is for a single step. You will go from here. You'll go from here to here because you're calculating the force at this point. Now, if you want to take two steps, then let's say we do it at dt by 2 first, and then again dt by 2. So in that case, what will happen is, now I'm going to draw with a green dot. You start with here, you start at this point. Then after dt by 2, you will be here. Again, you calculate the slope of the line, slope of f over there. So you see the slope is higher, and so you calculate this. And then you, based on this slope, you take the next step, and that will take you over here. So you can see now you're closer to the actual line where you want to be. And we can assume that the difference between these two, the green dot and the red dot at time t plus delta t, dt plus dt, that is proportional to the error. So we'll say that this difference is proportional to the error. So then this is how you do the two-step. You first take the first step just like this, but only thing it's dt by 2. Now you calculate the force again. The force is calculated at the midpoint, so it's at x1 and v1. And then based on this force, you calculate the velocity over here. And so you get x I prime 1, x v I prime 1. And very often velocity is the one that we want to really keep track of. So what we can do is we can just say that we should use a time step dt which is small enough so that this error is less than some specified tolerance. So by doing that, your velocity will never become too large in one given time step, and then the system will not become unstable. So I showed that last time. We'll look at it again. And this is what I started talking about, that if you want another way of increasing computational efficiency, then you can do what is known as binning. So let's say you have a large system with many particles, then you really don't need to check the whole domain. Let's say some particle over here, you don't need to check in the whole domain to see whether there's a collision possible or not. So usually what is done is that, let's say for example, if a particle is in the green box, then we will check only 4 closed boxes to check for neighbors. And if you are given any particle position x and y, then it's easy to calculate what is the bin number for each of them by doing this simple thing. So you can easily put all the particles in a bin where I cell is numbered 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you have numbered the cells in some order, and then you say what is I cell? This is trunk. Trunk means look at only the integer part of x divided by delta. Look at only the integer part of y divided by delta and multiply by n bin. N bin is the number of bins in one direction. Multiply by n bin plus 1. So that will give you the thing. So if x is in this bin and y is also in this bin, then what you'll see is this is 0, this is 0. So you'll have 1. In fact, we'll try it out for a specific example of how to do the binning. But the basic point here is that by doing this, you simplify this process quite a lot, because you're not now trying to find out the neighbors by looking at every particle, but you're looking at only particles in a small region of the domain. So this number becomes much smaller. So instead of n part squared, it may be something like just 50 squared or something like that, and then that doesn't increase with the total number of particles. So let's look at the example. So supposing you have this. Okay, now you are all paying attention. So I want you to tell me, for the first particle, which cell is it in? So let me just explain what is there. In this problem, there are only 4 bins, 1, 2, 3, and 4. The width of each bin is 5. So this distance for each bin, they are square bins. So each of these dimensions is just delta. And that delta is 5. Okay. So now I am giving you that there are 5 particles. The X position and Y position is given. And I want to fill in this column. So can someone tell me which one for the first particle, where will it be? Just to reiterate this function, trunk means look at only the integer part, and n bin over here is 2. So can anyone tell me where will be particle 1?
For fourth position.
4, correct. Can you explain why?
X is given, delta is given, x by delta 6.2 by 5. Then truncating the decimal places 1 plus then trunk y by delta. Then that also will be 1 into n bin will be 2 plus 1. So 4 will be the answer.
Correct. Perfect. And if you just look at this particle, since this is, let's say, if you want to look at it in terms of the x and y coordinates, so this is, I should have drawn this. This is y, this is x, this is 0, 0. And if you look at this, because it is, this delta is 5, this point is 10, 10. And this point is 5, 5. And this is of course 0, 10. I'm sorry, yeah. This is not 0, 10, but it is 10, 0, and this is 0, 10. So this is xy. So like this, you can see clearly that this is 6.2 and 8.9. So this particle will be maybe somewhere over here. So this is particle 1. And so obviously it's in I cell 4. Now you look at this 1.6, 3.9. This particle is going to be somewhere here. And you can check that x divided by 1.6 by 5 truncate is 0. 3.9 divided by 5 is again 0. So this is going to be in 1. Now look at this 6.8 and 7.5. Well, both of these are greater than 5. So again, this will be somewhere here. This is 2. This particle is 3. So again, you see this divided by 5, 6.8 by 5 will give you 1 point something. So trunk is 1. 7.5 divided by 5 will give you 1 point something, again 1. So 1 plus 2, 3 plus 1, 4. So this one is also 4. The third one, again, for the same reasons, I'm sorry. The fourth particle is also going to be here. And now here you can see for the fifth particle, x is 4.3, y is 7.8. So it means the fifth particle is somewhere here. And if you do the calculation also, you'll see that 4.3 divided by 5, that's less than 1, so this is 0. 7.8 divided by delta, that is 1 after truncation, times 2 is 2 plus 1, 3. So this will give you 3. So if you're given xy coordinate, it's very easy to find out which bin the particles are going to be in. And then once you have that, then you can use linked lists and put them all in this kind of 2 vectors. One is called head and the other is called L list. So the head contains the particle number of the last particle that is added to the cell, and L list contains the list of particles in each bin. And it's done in such a way that the particle number of the next particle is just L list of the current particle. And if IPN is 0, that is the end of the list. So I'm going to show you exactly how it's done. And you can store all this information of which particle is in which bin by just using these 2 simple vectors. So I think we'll go to actually looking at all this. What is the what is this linked list and all this stuff a little bit, so that we are not going to probably do the programming ourselves, but we would like to, I want you to at least understand what is inside these programs for doing the computations. So which is why I'm going through all this, but we don't want to treat everything like a black box. So this is, let's say, I'm going to just do one example to show you this linked lists. So what are the linked lists? Basically, it's basically for efficient storage and retrieval of bin dash particle information. That means that I should be able to find out which particle is in which bin, or alternately given a bin. So if I'm giving a particle, you should tell me which bin it is in. And if I'm given a bin, then I should be able to tell you the numbers of all the particles which are in that bin. So we are calling the bins ICEL, and we are calling, I guess the particles will be just IP. So this is what it is. So I'm going to number the cells like this, or the bins: 1, 2, 3, 4, as we had done before. So this is a simple problem. And then let's suppose I put this one particle over here, 1, 2 particle here, let's say 3 is here, and I'll put 4 also here. Let's say 5 is here, 6 is here, 7 is here, 8 is here, 9 is here, and 10 is here. So the particles are all distributed. In bin 1 there are 3 particles, in bin 2 there are 2 particles, in bin 4 there are 5 particles, and bin 3 0 particles. Okay. Now how will I keep this record? I mean, through the first formula with the truncation and all this, I was able to find out in which cell things are. Okay. And so now we would like to find out how to do this. And so for each particle, I want to find out so now suppose I'm given all the positions. So the first thing is that I want to say that, as I said, there are 2 vectors that I want in this linked lists. One is called head. Okay, so this is a matrix. The length of this is the total number of cells. Okay, length is a number of cells. And so, you know, the index will be I cell. I cell goes 1, 2, 3, and 4. So what this, as I said before, this, there will be a number in here which will tell us which is the number of a particle which was last put into the cell. So, you know, if you say head of I cell 1, this one will give you a number, and that number will be a particle number in that cell. So, you know, in 1 it could be either 2, 6, or 8. For 2 it will be 5 or 9. For 3 it will be 0 because there are no particles in there, and for 4 it will be. So initially what you have to do is, okay, and then so let me say that what is the second list, and the other one is called, the other matrix is called L list, and this has, you know, a large number of cells, and this length is equal to the number of particles. Okay, and so it will be 1, 2, this is the particle number. Okay. Now, what is the algorithm? So you consider particles, go particle by particle. So IP going from 1, 2, 3, all the way up to the number of particles. So you take it one by one. Then the first step is calculate the cell number. So if you are given the positions of the particle, so then we know the formula for calculating that. So xi divided by delta plus divided by delta into n bin plus 1. So this will give me, so for particle 1 I will get now what is the I cell number. So this is the first step. The second step is you write down that the L list of IP is just equal to the head of I cell, and then the third step is that head of I cell is equal to IP. Okay. So what we are doing is something really simple. First is you did, and in the previous when I was looking at the presentation, we know how to calculate this. So you know the I cell. So then what you do is you go to the head of I cell. Now let's say your I cell number is 4. then what is the value of head over there? That you put into for IP equal to 1. IP is 1, whatever is the head of I cell 0. If it's the first particle, then all will be 0. And then, so you're shifting whatever is the particle over here, you shift it to L list, and then whatever is the new particle, you put that in that bin position. Okay, so it's a very simple algorithm. Now in our case, we don't have to do this calculation because I've already done the calculation and put it in all the bins, so we know what it is. So first what I'll do is I'm going to start, you have to start like this, put zeros in head of I cell. Okay, then let's look at particle 1. Particle 1 is in particle 1 is in I cell 4. So I cell is 4. So head of 4 is 0, and that is equal to L list of 1. So you move this from 4 to 1, and now head of 4 must be equal to IP. So now instead of 0, I'm going to put this as 1. Now let's go to the second particle. Second particle is in I cell 1. So now this is also 0. So I'll move 0 to this point, and now I'll move, instead of 0, I'll put the particle number, which is 2, over here. So now this has become 2. Now let's look at particle number 3. That's again in 4. So you look at 4. Oh, this is 1. So this 1 has to be put over here. And in 4, that particle number is 3. So I'll put 3 over here. Now let's look at particle 4. Where is that? Oh, that is also in 4. So now I'm going to move 3 from head into L list. And now instead of 4, I will put the particle number which I'm considering right now, which is 4. Then let's look at particle number 5. Oh, that's in 2. So 2 over here, if we look, that is 0. So I'll move 0 for the particle number 5. And then I'll replace over here 0 by 5. So I'm just doing this. L list of that particle number, whichever I'm considering, is equal to whatever is the head of the particular cell. And then I'm putting head of that cell to be the particle number. So we've reached 5. Now we'll go to 6. 6 is in 1. So I shift, first step is L list of 6 must be equal to head of 1, which is 2. And in this, instead of 2, I'll put whatever particle that I've just found, and that is 6. Then I'll do one more. 7 is in 4. So again, you go there, whatever is in the head of for position 4, I shift to 7, so that becomes 4 here. And in here, instead of 4, I put 7 because that's the particle number. Then where is 8? 8 is again in 1. So this head of 1 is 6. So 6 comes over here. And instead of 6, I put 8. Okay. So now Can someone tell me 9? What should I do for particle number 9?
Sir, 9 comes in block, what we can say, in the
So first look at L list. So L
yes,
list of 9 is what? So yeah, 9 is in
2.
set number 2.
Yeah, set number 2.
Head is
So
5.
5. So 5 will be written below 9 and
Yeah.
9 will be written below 2 in the ICL head.
Correct. Okay, and then for 10, 10 is in 4.
10 is in 4, so head is 7.
7.
Correct. So 7 has to come into 10. You have to move 7 into L list. So that comes here. And then you remove 7 from here and replace it by
10.
10.
okay. So now if you look at these two matrices, you know what you will find is that the particle number comes only once. It comes only once in between these two matrices. So if you see, this is 1 is over here, then 2, 3, 4, 5, 6, 7, and then 8, 9, and 10 are there. Now, if you remember, since we went from 1 onwards, so really the last particle to be put into the bin was particle 8. That's why it's coming here. The last particle over here was 9, so that's why it's coming here. And the last particle to be put in here was 10, so that's why it's there. Now, how do you find out? So this is how you will fill these. So this storage is fine. Now, what use is this? So how would you go backwards? So if you remember, so if you want to what are the particle numbers IP in any bin? How would you do it? So first, the way you do it is that IP1 is just equal to head of I cell. So that is the first step. And then IP of n plus 1 is just equal to L list of, let me write this nicer, IP subscript 1 IP n plus 1 is just equal to IPN. Okay. So you keep on doing this recursively until IPN is equal to 0. So this is the two simple steps. Okay, so now supposing I want to find out particles example, which particles are in bin 4. How would you do it? Well, I cell is 4. So first you go to head of 4. So your IP1 is just head of I4, which is 10. Correct? Now what I can do is I can find out what is IP2, which is L list of IP1. What is L list of IP1? IP1 is 10, so L list of 10 is 7. And then IP3 is L list of IP2, which is equal to, so what is L list of 7? L list of 7 is 4. Then IP4 is just L list of IP3. We know IP3 is 4. So what is IP of IP4? L list of 4 is just equal to 3. And then IP5 is equal to L list of IP4. If you look at this, this is of 3. So this is equal to 1. And then IP6 is equal to L list of IP5. IP5 is just 1. So if you look at L list of 1, it is 0. So this ends the list. So in this way, I can easily find out all the particles in 4, and you can see I've got all of them. 10, 7, 4, 3, 1. Here it is 10, 7, 4, 3, 1. Okay. And what I'm doing is I go to this 4, so I've got 10. So I come to here, I get 7. Then from here I go to 7, I get 4. Then I go to 4, I get 3. Then I go to 3, I get 1. And I go to 1, I get 0. So I'm just jumping from particle to particle. And there is a link between the particle number, what is stored in the L list, and in the particle number. So this is a very, very efficient way of storing things, and you can easily recover. So can you do this exercise now for, let's say, bin number 2? So for bin number 2, can someone just orally tell me by looking at this? What is IP1 for bin number 2?
9.
It's 9, sir.
9, correct? And then if you want to find out the next one, then you go to IP of 9, I mean L list of 9.
It's 5.
5.
So you go 9 and 5, that's it. Similarly, if you want to look at 3, well, it's 0, so finish. There are no particles there, so straight off. And then if you want to go to 1, you start with 8. So that's the first particle. Then you go to 8 over here, 6 is the second particle. And then you go to 6. And so you have 2 is the last particle. And then you go to 2, you have 0, no more particles.
Zeros.
Correct? So this is the great thing. So you can store you can bin all the particles, you can record it like this, and then okay. So this is one more way of doing things in a efficient way. Okay, so let me go back to the examples that we were doing, and again, did any of you try and put your WSL on your systems, or if you're using a Mac, and so then you don't have to do anything?
Yes, sir.
Or if you're using Linux, if you have access to a Linux computer, also no problem. So let me just run through the sort of demo programs again, which I was doing there for the soft particles. this is all, again, I think it's already up there. So EX1, if you remember, that was the same as what we had done for the hard particle. Actually, all these are the same as what we did for the hard particle. This is just collision of two particles. And here it is. The only thing that we wanted to note is that the collision time is slightly more. The other one was 0.86. This is 0.88 because the collision is of a finite duration. And you can see that the velocities, the green arrows are what you get from the hard particle. So for the soft particle and hard particle, there are some minute differences. And that is to be expected since your collision durations are not zero in this case. Okay, so this was one thing that we did. And I showed you this also. So this is the neighbor list which we saw in the presentation, and you can see that it's going from 1 to 1 in parts, I going and j going from I plus 1 to in parts. So this is one of the expensive steps. Then this is just moving it, and here is the Euler method, v times dt and force times dt. And here is the calculation of the force. So we just calculate what is alpha. So alpha we can calculate as 1 minus d, and then we can calculate the velocity, normal velocity, which is d alpha, and then from there we can get the force. It's just kx times alpha minus kv times d alpha by dt, which is velocity, normal velocity. So this is a very simple program and it does the job. Now if you have just this, I integrated it only up to the first collision. That's why there is no. Then what I tried to show you is that if I just do exactly the same thing with a relatively large step, and if I run this, and you'll remember I showed you this thing, that your kinetic energy keeps increasing because the system is just unstable, and you see the velocity is blowing up and kinetic energy also blowing up. So you see this is now a totally, I mean, this system is, these results are absolutely meaningless. They don't have any meaning because the computation itself is unstable. However, if you modify that program and instead of using just the Euler method, if you use now, you can see that I'm doing it. The first step, I'm calculating it at dt by 2, and then I calculate what is the error, and then I make the correction. So if the error here I see, while the error is larger than the tolerance, then your dt is reduced by a factor called fac, where factor is 0.8. So I keep on reducing the time step by 0.8 until the error satisfies this limit. And so if I do run PC, so it's exactly the same program. The only thing now I have put this, and all the parameters are exactly the same. Only thing is now I have this predictor corrector in there, so it adjusts the time step so that there is no instability. And you can see that here now the velocities all look nice. The particles are not overlapping with each other much as required. And most importantly, the kinetic energy is constant because we have taken our parameter value to be, our coefficient of restitution to be 1. kV over here you can see is 0. Kx is 1000, kV is 0. That means coefficient of restitution is 1 and there should be no loss of energy. And in fact, kinetic energy is just coming constant. Okay, so we've done it for a long time, up to 18 seconds, and it's still fine. And this is just to show off that with the predictor corrector, this is how the kinetic energy is, the green line. And when you have no predictor corrector, your kinetic energy just blows up to some huge number. So this is a very simple way, and you can see the time step is not too, doesn't make much difference. Now, if we run the same thing for coefficient of restitution 0.9, same program, and then you can see that the velocities will decrease. Here you can see the velocities coming down, and of course the kinetic energy also falls with time. See, kinetic energy has fallen from 1.4 to something very small, about 0.07 it has come down to. But if you plot kinetic energy raised to power minus half versus time, you get a nice straight line. And then if you look at so this is the same thing but with gravity. So same program as the earlier one, but now gravity is added. Here you can see the particles have all settled down. Kinetic energy first increases because the particles are falling, but then because of viscous dissipation, the energy starts to reduce. We saw this even in the hard particle simulations. So this is what it is. And in the final one, all that this does is, this also has binning in it. So in this, I'll just show you how much time you save. So there are two programs. This is the one program with just the predictor corrector, which is called box PC. So you can see here, we do this dt by 2 and then calculate the error and so forth, and then reduce this factor and things. But for calculating the neighbor list, we are looking at all the particles. So we check with between every two particles. Whereas if you look at this box PC bin, you first make some map. This is the link list. And now the neighbor list is only, I go over the bins. So cell going from 1 to n cell. And then I check only the neighboring bins. The neighboring bins are given by this mapped C matrix. And so I check far fewer particles. So, if I run this, you'll see that here is the thing. It took about 1.385 seconds. And if you do the binning, this is 1.385 seconds, and this is the time for with the binning, it is 0.47 seconds. So, you can see that almost 1/3 the time it takes. And so you get a significant time improvement. And of course, for small systems, it doesn't matter much. But once you go to hundreds of thousands of particles, then you can have significant savings by doing these type of things. So we have now completed about 3 weeks of classes. In the next, I'm sorry, yeah, 3 weeks are completed. We have finished 9 lectures. And I'm close to, I think I'm going to spend another couple of lectures on tools, which will be introduction to lamps. And then I'll get you started on doing some of the simulations. Please try and see, you can look into these programs and try and see if you can run them. They will give you a little bit of insight into how these programs are developed, and so if you want to ever develop such a program, it will be very easy for you to do it. Okay, so with that I will end, and I'll see you now on Monday morning.